application. Application of Gauss law or theorem, you can say. So the first is to find out electric field. Of infinitely long uniformly charged straight conductor, just like a wire. So suppose if that your infinitely long uniformly charged straight conductor is here like this in the form of wire. Let me draw a little bit straight, okay, like this. Then what happened? We don't know the length because it is infinitely long. So we don't know the total charge present in that infinitely long conductor. So rather we know lambda. What is this lambda? Lambda is nothing but this is the surface linear charge density. Linear charge density. We may also call it this as charge per unit length. Charge per unit length. So instead of that per unit, let me write divided by. Okay. So if you want to find out electric field at this point P, so you will call it this point P as a point of observation, because we want to find out electric field E due to this infinitely long straight charge conductor. So let's take it that the charge present here over this linear conductor be taken as positive. Okay, so if you want to find out the electric field E here, now we need to develop a Gaussian surface. What is this Gaussian surface? This Gaussian surface is an imaginary surface. Now in order to apply this Gauss law, we need to envelop or enclose this charged surface by a closed surface. That imaginary closed surface similar to this charged conductor, to enclose the charged conductor where at every point of that Gaussian surface the electric field remains constant. That surface we call it as Gaussian surface. So as a charged conductor or this straight conductor is just in the form of a wire. In the form of wire means it is just like a cylindrical form. So we need to develop a Gaussian surface, Gaussian cylindrical surface passing through this point of observation P, where you want to find out your electric field E. So let's draw a Gaussian cylinder, and this is at a distance R. Now when we draw this Gaussian surface, then this will be the radius of that cylinder. So what happened passing through this? Let's draw a Gaussian cylinder like this. So this Gaussian cylinder, let's take it, this Gaussian cylinder has its axis like this, and the length of this Gaussian cylinder is taken as L. Now what happened? Let's try to find out the electric field E over here. Then what happened? Electric field E will be equal to, we need to find out that electric field. This is the application of electric field E. So your electric field, as being this is a positive charge, your electric field E will be perpendicular to this curved surface of the Gaussian cylinder, and let me mark this as capital E vector here. So this will be your capital E vector like this. Now here we can have three surfaces. The first one is this circular face, another second one, this is also the circular face, and the third one is the curved cylindrical surface let's name it these as 3, surface 3. So if we want to find out the total electric flux in order to apply your Gauss law, then what happens? We need to find out electric flux over the surface 1, over the surface 2, over the surface 3 separately, and we have to add it up so as to have the total electric flux. Now see, for this electric field E is radially outward. Now for this surface 1 and surface 2, your surface, for this surface 1, the surface area vector or the surface vector, this ds will be along this, radially outward. For this surface 2 also, for the surface 2, this will be also along this ds vector. For this curved surface, your electric field E is also along here, and your surface vector will be also along this. If you take it this as a small surface, but I should not draw it like this, rather I have to draw it in this way. So what happened? This small surface has ds and its area is ds, so the area vector will be perpendicular to the surface and it will be radially outward, so as we have to take that as positive. So this surface, there are many surface area here like this, pointing outward like this, all over the curved surface of the cylinder. Now, just to find out the total electric flux, let's try to find out the electric flux over these 3 surfaces. So your total electric flux phi will be equal to what? Phi 1 due to the circular surface. This number 2 electric flux due to the second surface, which is circular in nature, and the third one, total electric flux due to passing through this curved cylindrical surface, surface 3. For this curve 1, that means circular faces, what happened? As your electric field E is here like this, and the surface area vector ds vector is along this, so the angle between them is 90 degree. Electric field E and ds vector are perpendicular here for this surface 1 and surface 2, same thing. Electric field E will be here like this, on this also E like that, somewhere here also on the surface, and so the angle between the electric field E and the ds vector, this will be 90 degree. So when we try to find out total electric flux for this surface 1 and surface 2, what happened? As the angle between them is 90 degree, cosine of 90 degree will be coming out. Cosine of 90 degree means what? 0. So these two vanishes. And so only the total flux what remains is due to contributed by the surface third one, the third curved surface, I should say. So what happened? As the distance from here to here, this is just like the axis of the cylinder. So what happened? Distance at every point on the curved surface of the cylinder will have the same distance r, and so your electric field E will be also remaining constant. So that electric field E, let me write like this, E over the whole surface, and this will be ds like this. So as I told you that this E and ds are along the same direction, so angle between them is 0, and moreover E is constant at every point here because the distance from the axis, or rather from the charged conductor lying at the axis of the cylinder, these are at the same distance. So what happens? Your E will be also constant. So we will take it out, that E outside, and we need to integrate the whole surface of the curved surface area. Now when you cut this cylinder, and if you open it, then it will be just like this. Let me take one paper. I'm not having that one. Okay, let it be. So what happens when you cut somewhere here, then and if you open it, then it will be in the form of rectangle, right? So of whose area will be what? Length will be no doubt L, and breadth will be what? Breadth will be when you open and unfold it, then this length will be what? The circumference, right? So circumference means it will be twice pi r. So this area will be the total area for this whole curved surface will be area of just like a rectangle, and the length is here, breadth will be what? The circumference. So let's write it like that as E into twice pi r into L. And as per Gauss law, what happened? Your electric flux, total electric flux, is the surface integral over the whole surface is equal to what? 1 by epsilon naught times the charge enclosed by this closed surface. So the total charge enclosed by this closed surface we can certainly find out from that linear charge density. The total charge is not given, it is an infinitely long one, so we need to find out the total charge enclosed by this closed surface. And I said that this charge is equal to what? L into what? Lambda. So that will be the total charge enclosed by the cylindrical Gaussian cylinder of length L. It will be what? Lambda times L. So this is the total charge enclosed by the closed surface. So neglecting about this phi, we want to concentrate here in this equation because we want to find out the electric field E. So from this equation, what happened? Your L will be cancelled with L, and so from here your electric field E can be expressed as what? E is equal to 1 by twice pi epsilon naught lambda by r. So this is the magnitude of the electric field E due to that infinitely long, uniformly charged, straight conductor. Okay, so and if you want to write it in the form of vectorial, in the form of vector, or rather in the vectorial form, then you can put it here as r cap here like this, where r cap is in the direction of electric field E, or rather you can say it will be radially outward perpendicular to its axial line. You can call it in that way, you can say it in that way. So this is all about your electric field E due to that infinitely long straight current conductor. Now next application is about infinite number 2 electric field due to thin infinite plane charge sheet. So let's draw that infinite plane charge sheet. This is infinitely long. It can be extended in along the 4 directions like that. So what happens if this is the charge and the total charge that is residing onto this thin infinite charge sheet we can't find out, but we don't know also, rather it is what we know what sigma. What is this sigma? Just like in the case of the previous one, lambda, linear charge density, we call it this sigma as what? Surface charge density. Sigma is what? Surface charge density. That means charge per unit area in this case. So if we know that particular area, then the total charge residing in that on that area can be found out by multiplying each area and the surface charge density. Now to find out the electric field E for this due to this infinite plane charge heat, now if you want to find out that electric field E at somewhere here at a point P, so this point P is a point of observation at a distance of what? R, let's say from the infinite charge sheet. So let's take it that this infinite charge sheet is carrying positive charge like this. Let me not draw all. Okay. Now then what happens? We need to develop a Gaussian surface. Either you can take it this as a cylinder, and we can draw a Gaussian cylinder over here like this. This is at a distance R, as I said. Let's take it this point as O, and let's take it that this distance is R. So we need to have like this much. Distance R, distance R. So let me draw a little bit longer. Since it is a little bit short, so let me draw a little bit longer like this, so that I can draw it somewhere here, and this will be the Gaussian cylinder. So this is your point P. Now this is the charge body, so this sigma plus will be here. So when we want to find out the total charge enclosed by this closed surface or closed Gaussian cylinder, then we need to take this area. So let's have this area as area A, and that area A, if you want to find out the vector, then your area A vector will be in this direction. So let me call it this as A, and let me write as A vector like this simply. And this also, so let's take it that this is also along this A, and this distance is small r, on this side also small r, from somewhere here. Okay, so here also similar to that previous one, we will have three surfaces. One, the circular surface on the left side. Two, the circular surface on the right side. And three, the third surface, that is what? The curved cylindrical surface. So if you want to find out that total flux, then we need to find out what? That electric flux due to this surface 1, electric flux due to the surface 2, electric flux due to the third surface like this. But for this third surface, electric field E will be along this. Now just let me tell you, as it is perpendicular to the electric field to the surface, so electric field E comes out perpendicular to the surface, to the charged surface. So what happens? Your E will be coming out like this, perpendicular to the surface. So your E will be also in this direction. Here also same thing, your E will be along this. So what happens for this surface 1 and surface 2? What happens? Electric field E and area vector, they are along the same direction. But for this third surface, what happens? Electric field will be along this like this, but the surface will be perpendicular like this. So your electric field E here, you can call it here, you can draw it, electric field E here, and your surface Here, let's take a small surface, okay, somewhere here, like this, that surface. So ds vector, the angle between them is 90 degree, and so what happened as the angle between them is 90 degree between electric field and this ds, what happened, cosine of 90 degree will be coming up and it will not contribute to any of the electric flux. So this will go to 0, and so the contribution is due to this surface 1 and surface 2. So as we have taken that this surface area is capital A, so your total electric flux will be equal to what? E A for this also, for that also it will be EA. And this, as distance is same, what happened? The electric field E here and the electric field E here, the magnitude of the electric field E at these two surfaces, surface 1 and surface 2, will be remaining constant. I mean the magnitude will be remaining constant. So it will be what? EA also here. And we can write this as twice EA. And according to your Gauss law, this is surface integral. This will be equal to 1 by epsilon naught times the charge enclosed by this Gaussian surface. Gaussian surface is our closed surface now. So 1 by epsilon naught times the Gaussian surface, the charge enclosed by this Gaussian surface. If this is having the area A, then this must be also having the same area A, right? So what happened? Your sigma A charge will be equal to area times sigma. So the charge enclosed by this Gaussian surface will be only this portion that is enclosed by this Gaussian cylinder. So it will be equal to, the total charge will be sigma A only. So likewise, as we did in the previous case, let's try to concentrate the equation relating these two, not this one. Let's neglect it. So what happened? Your AA can be cancelled, and what remains is what? Your electric field E will be equal to what? Sigma divided by twice epsilon naught. This is the magnitude, and if you want to find the direction, then it will be what? Radially outward, or you can write it in the R cap. R is what? This is a distance of the point of observation, so it will be along that R vector. If it is denoted by R here, okay, then it will be giving you the vector form of electric field E. Now, point to be noted here is that what happened? Here in this equation, it is independent of this distance R. Had the point of observation P to find out the electric field E here, if it is somewhat here close also, it will have the same value. Had it been far away from this point, somewhere here, the distance of R will be more, but as it is independent of the distance R, what happened? This E will have same value. So this point we will have to be related again in the case of, while we are learning in the case of capacitors, okay? Try to remember at the time of capacitor. I will surely ask you. Now next, what happened? Point to be noted, another one is what? This sigma by twice epsilon naught. When we discuss this infinitely charged plane sheet, we take this plane sheet as a thin infinite plane sheet. Thin is there. Okay. Why thin? Because if it is just like a thin sheet, that means we may assume that charge resides only on the surface. We know it, no? Then the one charge may be half. Suppose if you take it as a point charge, then the half of the charge, that means hemispherical portion of the charge will be on one side, another hemispherical surface of the charge will be on the other side. So when we take it the total charge, then we have to take it as a single charge is residing onto this sheet. So we take it like that. But if there is an appreciable thickness of this charge sheet like this, in this manner, if there is an appreciable thickness of the charge sheet, then what happens? The two charges like this, charge resides only on the surface. Charge enclosed will be what? Charge onto this side, and charge residing onto this side must also be taken into account. So what happens when total charge, and in that case, what happens if it is if the plane charge sheet is of finite thickness, then what happens in that case? Your phi will be twice EA not up, and this will be affected. Two will be coming up. One charge on this side, another charge on that side. The total charge will be 2 times of this. So it will be equal to what? It will be equal to what? This 2 will be factor 2 will be there, another factor 2 for that 2 it will be here. 2 means 1 on this side plus the charge on the other side. So 1 plus 1 it will be 2, so this will be 2. So when you cancel 2 here, then your electric field E will be equal to what? Sigma by epsilon naught. See the difference? Okay, when the infinite plane charge sheet, if it is very much thin, then what happens? It will be having electric field E will be equal to sigma by twice epsilon naught. When the infinite charge sheet is having a finite thickness, appreciable thickness, then your electric field E will be equal to sigma by epsilon naught. There are some other points or cases can be also considered, but let's do it that one later on. Now let's try to find out the third application. Electric field due to a what? Spherical charge. So let me remove these things. So what is what? Number 3, electric field due to a charge, or rather uniformly charged spherical shell. When I say shell, it is hollow sphere. Okay, it is not a solid sphere. So let's take it that this is a sphere of whose center is here at O, and this is charged spherical shell. So let's take it this radius of this charged spherical shell as capital R, and let's take it that the charge residing onto this spherical charge be taken as Q. Now there will be 3 conditions for this also to find out electric field E. So let's try to find out separately. One, what happens well outside the spherical charge shell. So let's take it this as P for the first one. So that means we can say outside the spherical shell, charged spherical shell it should be. Next, we can bring this point of observation. We want to find out electric field inside the charged spherical shell. Third, we can find out electric field E onto the surface of the charged spherical shell. So let's try to find out for this the first one. That means outside at any point electric field due to this uniformly charged spherical shell outside it. So what happened? Passing through this, we need to have a Gaussian surface. As your charged body is a spherical shape, your Gaussian surface must be also of the similar shape. So it will be, you need to develop a Gaussian spherical shell here like this. And let this radius, or rather the point of observation for this point P, be denoted by R. And if you want to draw, if you want to mark it in the form of vector, then you can have as a position vector R like this. So naturally, what happened for this? We need to take it that the charge reside here is what? Positive. Let's assume. No doubt we can also do it for negative charge also. Okay. Yeah. If it is positive charge, then what happened? Your electric field, okay, will be radially outward from it. Got it? When the charge, when we consider the charge here as spherical charge, and if the point of observation is outside, then we have to assume that this whole charge is supposed to be concentrated at its center. Now we need to find out electric field E there of this point of observation P well outside the charged spherical body. What happened? Your electric field E will be along this, and if you take a small spherical, small infinitesimally small surface ds, then that ds will be also having the same direction here like this. So your E vector and ds vector will be along the same direction. So what happened? And moreover, over this, this being the spherical surface, the distance from the center of the charged body to any point on the Gaussian cylindrical surface, that will be having the same distance, and so what happened? Your electric field E will be constant. Let's take it is over the whole surface as Gaussian surface as the surface is. So your flux, total flux phi will be equal to what? Surface integral of E dot ds over the whole surface S. This will be equal to what? Your E is constant, and so you have to take outside the integration, and then you need to do integration of that small surfaces over the whole surface S, and no need of putting the vector form now here. So as this cos of theta comes up, cos of theta will be 0 as E vector and ds vector along the same direction or parallel. So theta will be what? 0 degree. Cosine of theta or cosine of 0 degree will be 1. So no need of putting there. So or your E vector, no need of writing again. So your total surface area for this will be equal to what? 4 pi r square. 4 pi r square like this. This is the whole surface area of this Gaussian cylindrical spherical surface. So this will be equal to, by Gauss law, it will be equal to 1 by epsilon naught times the charge enclosed by this Gaussian spherical surface. So that charge will be equal to what? Q. So let's write it like this, Q. So as we want to find out electric field E at that point P, your electric field E can be expressed as what? 1 by 4 pi epsilon naught Q by R square. So this is the magnitude of the electric field E due to this Gaussian, due to this spherical charge body at the point P of distance r from it will be equal to this, magnitude will be this. And if you want to write it in the form of vector, then E vector will be equal to, this is the magnitude, and you need to put one r cap here. R cap is unit vector along the direction of r vector. That's all. Now then, what can be found out from this again? So what happened? This is just like the electric field due to a single point charge, right? So now what happened? What I said, when if the point of observation is outside the charged body, then we need to assume, or we need to what? Suppose to that the whole charge is concentrated at the center of the spherical charged body, as I said. So if this whole charge is concentrated, supposed to be concentrated at this center of the spherical charged body, then it will be just like the electric field due to a single point charge. One here, due to this single point charge, electric field at this point P of distance r will be equal to like this, right? Now number 2, inside, number 2 is what? Inside the charged spherical seal. In that case, what happens? Your phi will be equal to what? surface integral of E dot ds. This will be equal to 1 by epsilon naught times the charge enclosed. This is a Gauss law. But if you take it some point of observation inside the Gaussian surface like this is the point of observation for a second. Okay. But then what happened? Your Gaussian surface should be drawn passing to this point of observation like this. This will not to be discussed further. Why? Because the thing is that charge resides only on the surface, we know it, right? So what happened? Through this Gaussian surface, no charge is enclosed. Charges are residing outside, right? Onto the surface of the spherical body. So if the point of observation is well within the charged spherical shell, then what happened? This charge enclosed will be equal to 0. This part is equal to 0, and so whole of this will be equal to 0. Even though this has finite surface, what happened? Your electric field at that point inside the what? Charged body, that will be equal to 0, right? This is a condition for what? That of electroshielding. It has been said that during lightning, it is much safer to stay well inside the car than to stand beneath the tree, right? Because car is just shielding, and all charges will be residing outside the charge outside the car. And if you are staying inside, whenever there is a lightning strikes onto the car, then what happens? You are well outside the electric field, so you are safe, no shock. Okay, that is known as electroshielding. That is the case for this one, right? Now last one is what? If you are taking onto the surface of the charged spherical shell. So let me simply write on the surface. On the surface of the charged spherical shell. Let's take it that in that case, so let's remove it, all these things, so that maybe clear more. Okay, you will understand more while visualizing. Now the radius of this charged spherical shell is r. Our point of observation is also at this point on the surface, so this is our point of observation. Your r vector will be now equal to, magnitude will be equal to capital R. So your E vector, if you take a small surface here, your ds vector is also here in this direction, and your E vector is also along the same direction, because electric field E comes out perpendicular to the surface, right? So in this case, your flux phi will be equal to what? E dot ds over the whole surface. Let's take this as S. This will be equal to what? Your electric field E onto this surface will be same. For this also, you have to consider that the charge is residing here onto the at the center. So in that case, E will be same, and your total surface area will be equal to what? After this, ds surface area of this will be equal to what? 4 pi capital R square, where R, capital R is the radius of this sphere. So this will be equal to what? 1 by epsilon naught times the charge enclosed by this surface. So we have to take it that the Gaussian surface is also having here the charge enclosed for this onto this surface, and outside the surface we need to take it that the whole charge is residing at the center. So the charge, this will not be equal to 0, rather this will be Q. So your electric field E from this equation, your electric field E will be equal to what? 1 by 4 pi epsilon naught Q by R square. This is the what? Expression of electric field E. Now, if you want to write it in the vectorial form, it can be, okay, as we did in the previous cases. Now here it depends upon R, electric field E depends upon R. So if you are going to draw the electric field E over versus the distance of the point of observation, your electric field E, magnitude of electric field E, I can write it. This is the origin. Let's take it that this is along the x-axis and along y-axis like this. Okay. Now let's take it that this is the center of the spherical charge body, and somewhere here is your capital R, and when it is very far away it will go like that. So what happens when you go when you take that electric field in the case number 2 inside the charge, spherical charge, what happened? Electric field E was 0, right? So whether you are taking the point of observation here, here, so all within the spherical charge, electric field E is 0. So your electric field E 0 means your graph will be onto this x-axis to this. Got it? When what happen is equal to R, then it will give you the maximum value, this one. So let me mark it here, somewhere here, this point, somewhere here. At a point R, it will be here. And this corresponding point, it is nothing but this is E max. Electric field will be maximum here when the point of observation is on the surface. When this R keeps on increasing, then being in the denominator, what happened? The whole will be decreasing. That means electric field will keep on decreasing. And moreover, this is what? Inverse square, right? So what happened? It will rapidly decrease like this. So your graph from here, when you go more and more outside the spherical charge body, more and more farther and farther, then your curve will go like this. This is the electric field versus distance graph. Okay, this is what I'm going to want to tell you. Okay, dear friends and dear students, for the home assignment and for that of some work that I need to give you, that will be given not through this live video classes, rather I will give you through WhatsApp. Okay, thank you.